There is a moment, and I want you to sit with this, when a spacecraft returning from the moon hits the top of Earth's atmosphere and the air around it begins to glow. Not red, not orange, white, a brilliant, blinding plasma white. The capsule is moving at 24,000 miles per hour. To put that in terms your body can feel, if you stood at one end of a football field and the Orion spacecraft was at the other, and it started moving toward you, it would reach you and pass through you before a single nerve signal could travel from your skin to your brain. Before you could feel it. Before you could know it had happened at all. That is how fast this machine was going. That is how fast 4 human beings were traveling on the evening of April 10, 2026, as they fell toward the Pacific Ocean after 9 days in the vicinity of the moon. And the air in front of that capsule, compressed by that velocity, heated to nearly 5,000 degrees Fahrenheit. That is roughly half the temperature of the surface of the sun. Think about the surface of the sun. Think about the thing that makes life on Earth possible. That great burning sphere 93 million miles away that provides every photon of energy that has ever warmed a field, grown a grain of wheat, powered a solar panel, or given a child reason to squint on a summer afternoon. Now cut that temperature in half. That is what the outside of the Orion crew capsule experienced for approximately 6 minutes on a Friday evening over the Pacific Ocean. And inside that capsule, for human beings, strapped into their seats, wearing their orange Orion crew survival system suits, listening to the roar of re-entry through the hull, feeling the G-forces multiply as the atmosphere fought back against their velocity, trusting completely and without any available alternative the engineers, the physicists, the material scientists, the test pilots, the flight directors, and the generations of hard-won knowledge accumulated across 60 years of American spaceflight. All of it encoded in a heat shield made of a material called avcoat, a cork and epoxy composite that was first developed for the Apollo program more than half a century ago and has now been reimagined, remanufactured, and retested for this exact moment, this exact fire, this exact return. This is the story of Artemis II. This is the story of a mission called Integrity. This is the story of the most significant human spaceflight event since the Apollo era, and what it means for where we are going next. But to understand the return, you need to understand the journey. And to understand the journey, you need to understand why it took so long to get here. Let us go back to December 1972. The moon, the Taurus Littrow Valley, a place of ancient volcanic rock and crater-pocked gray, regolith on the southeastern edge of the Sea of Serenity. Commander Gene Cernan of Apollo 17 climbs the ladder of the Lunar Module Challenger for the last time. He says a few words. He has written his daughter's initials, TDC, Tracy Dawn Cernan, in the lunar dust. He steps off the surface. He is the last human being to stand on another world. For the next 54 years, no human being will go further from Earth than low Earth orbit. No human being will leave the protective embrace of the geomagnetic field, that invisible bubble generated by the churning iron core of our planet that shields us from the worst of the sun's radiation. No human being will see the Earth as a whole object, hanging alone in the black, without the station or the shuttle or the Soyuz visible in the frame. 54 years. To put that in context, the entire Apollo program, from Alan Shepard's 15-minute suborbital hop in 1961 to Gene Cernan's departure from the lunar surface in 1972, lasted 11 years. 11 years from scratch to the moon. And then we stopped and stayed stopped for nearly 5 times as long as it took us to get there in the first place. The geopolitical urgency that had driven the program, the need to beat the Soviet Union, to demonstrate technological superiority, to plant a flag in the most visible place in the night sky, evaporated when the race was won. The funding dried up. The political will drifted elsewhere. And the moon, our moon, the same moon that pulled the tides of every ocean, lit the path of every navigator, filled the dreams of every child who ever looked up on a clear night and wondered. The moon sat waiting, patient as only a 4.5 billion-year-old rock can be. In the years that followed, the people who had built the Saturn V rockets, who had written the flight software, who had sewn the spacesuits, who had sat in mission control and coaxed 3 fragile human beings to the surface of another world and back, those people moved on. They retired. They wrote memoirs. They gave talks to school children who grew up to become the engineers who would eventually try to do it again. and the institutional knowledge, the hard, painful, specific, irreplaceable knowledge of what it actually takes to send human beings beyond low Earth orbit, slowly faded, like a song you once knew perfectly but haven't heard in decades. The tune is still there, somewhere, but you have to relearn the words. That relearning process is called the Artemis program. And on April 1st, 2026, at 6:35 in the evening Eastern Time, from Launch Complex 39B at Kennedy Space Center in Florida, the same launch complex that once sent Apollo 10 to the moon in 1969, it took a giant, irreversible, fire-breathing step forward. The Space Launch System, the most powerful operational rocket on Earth, standing 322 feet tall, taller than the Statue of Liberty from base to torch, taller than a 30-story building, producing 8.8 million pounds of thrust at liftoff. To generate that thrust, it burns through approximately 1 ton of liquid hydrogen and liquid oxygen every second. Every second, for 8 minutes, until the core stage exhausts itself and falls away over the Pacific. The ground shakes for miles. The sound wave, and people forget that sound is a physical thing, a compression wave, a force that pushes against your chest and vibrates your lungs, arrives at the press site about a second after ignition, like a physical reminder from the universe that you are witnessing something serious. And atop that column of fire and smoke and controlled chaos, a capsule named Integrity. And inside that capsule, 4 of the most accomplished, extensively trained, carefully selected, thoroughly scrutinized human beings on the planet. Commander Reed Wiseman, Pilot Victor Glover, Mission Specialist Christina Koch, Mission Specialist Jeremy Hansen. Let me tell you about these 4 people. Not just their credentials, though those are extraordinary. Let me tell you about them as human beings, because that context matters enormously for understanding what this mission means. Reed Wiseman is 50 years old. He was born in Baltimore in 1975, the same year the Viking 1 spacecraft was launched toward Mars. He is a Navy test pilot, which means his entire professional life has been built around the proposition that you climb into an experimental machine, push it to its limits, note carefully what happens, and either fix it or fly it again. He spent 6 months aboard the International Space Station in 2014 as part of Expedition 40 and 41. He then served as Chief of the Astronaut Office from 2020 to 2022, the person responsible for the professional development and readiness of every NASA astronaut. He knows this program from the inside out, from top to bottom, from the political machinations of Washington to the smell of the cockpit at T-0. His wife, Carol, whom everyone called Taylor, died in 2020. He is raising their 2 daughters alone. When asked in an interview why he takes such risk, why he continues to push toward things that could kill him, he said something quietly extraordinary. He said there are 4 human beings who have been put in a position to go explore something very unique and rare in this civilization, and he does not take that lightly. He flies, in part, for his daughters. He flies because he believes that showing them what human beings can do when they commit to something larger than themselves is worth whatever it costs him. There is something in that, in the willingness to carry grief into the sky, that is very hard to put into words. But it is real. And it was present, I think, in every single moment of this mission. Victor Glover is 49 years old. He grew up in Pomona, California, in a family where education was non-negotiable. He became a Navy captain, an F/A-18 Hornet pilot, a graduate of the Navy Fighter Weapons School, better known as Top Gun, and a test pilot. He was selected as a NASA astronaut in 2013. He flew to the International Space Station in 2020 on the first operational SpaceX Crew Dragon mission, becoming the first black astronaut to live and work aboard the station for a long-duration mission. He spent approximately 6 months there. And now, on Artemis II, he became the first person of color in human history to travel to the vicinity of the moon. In a country with the history that America has, with all of its complicated, painful, still unresolved history regarding who gets to participate in which endeavors, whose name gets attached to which achievements, whose picture appears on which commemorative poster, the significance of Victor Glover sitting in the pilot's seat of a spacecraft 4,000 miles from the surface of the moon is not a footnote. It is a headline. It is, in fact, a correction. A long, overdue, beautiful correction. Christina Koch is 47 years old. She grew up in Jacksonville, North Carolina. She earned a degree in electrical engineering and physics from North Carolina State University and a master's in electrical engineering. Before becoming an astronaut, she worked at the South Pole. Not metaphorically, literally. She spent a winter season at the Amundsen Scott South Pole Station, living in one of the most isolated, most hostile, most psychologically demanding environments on the surface of Earth. If you want to know whether someone can handle isolation, confinement, extreme temperatures, and the psychological weight of being very far from everyone they love, you send them to the South Pole. She came back from that. She became a NASA astronaut in 2013. In 2019, she launched to the International Space Station and stayed for 328 days, the longest single spaceflight by a woman in history. She participated in the first all-female spacewalk alongside astronaut Jessica Meir in October 2019. On Artemis II, she became the first woman in history to travel beyond low Earth orbit, the first woman to approach the Moon, the first woman to look out a window and see, not the curve of the Earth below, but the full gray disk of our nearest neighbor filling the glass. She said, after the lunar flyby, "I'm not ready to go home." That sentence contains multitudes. Jeremy Hansen is 47 years old. He was born in London, Ontario, Canada. He is a colonel in the Royal Canadian Air Force, a CF-18 fighter pilot, and has been a member of the Canadian Space Agency's astronaut corps since 2009. Artemis II was his first mission in space. His very first time off the surface of Earth was a 10-day journey around the Moon. Think about the audacity of that trajectory. Most astronauts spend their first mission on the International Space Station, 250 miles above Earth, in what is essentially a well-traveled commuter route by modern standards. Jeremy Hansen's first mission was 250,000 miles away. His presence on the crew is not incidental, it is structural. Canada contributed the Canadarm3 robotic system to the Lunar Gateway program, and as part of that partnership, Canada earned a seat on a lunar mission. That seat went to Jeremy Hansen. He became the first non-American in history to travel to the Moon. Humanity's return to the lunar neighborhood was, for the first time, genuinely international. Before the mission, Hansen brought a small moon pendant with him, a piece of jewelry engraved with the words "Moon and Back," containing the birthstones of his wife Catherine and their 3 children. He took his family's birthstones to the Moon and back. If that does not tell you something about what drives human beings to do the things they do, about the way love and ambition and the desire to show your children what is possible are all woven together into the same act of courage, then I do not know what more I can offer you. These are the 4 people who flew integrity. These are the 4 people who came home in a fireball on April 10th. Now let us talk about the machine that carried them. The Orion spacecraft has been in development for over 20 years. Its roots go back to the Constellation program, NASA's previous attempt to return to the Moon, which was funded in the mid-2000s and then canceled in 2010 by the Obama administration. The engineers who had spent years designing the Crew Exploration Vehicle, Orion's predecessor, did not go away. They adapted, they redesigned, they kept building. Through 2 presidential administrations that were broadly supportive and several that were ambiguous or hostile to the program, through budget cuts and schedule slips and contractor disputes and a global pandemic that shut down the facilities where the spacecraft was being assembled. Through all of that, the Orion program kept moving forward. The result is a spacecraft that is, in some ways, quite traditional and in other ways radically advanced. Traditional in the sense that it is a capsule, a blunt-nosed cone of aluminum, carbon composite, and titanium, not so different in basic shape from the Apollo command module that carried Neil Armstrong to the Moon. The capsule shape is not nostalgia. It is physics. When you want to decelerate from orbital velocity to splashdown velocity, you want maximum aerodynamic drag on the blunt end of the vehicle, pointing into the direction of travel. The shape that does this best, that dissipates heat most effectively while decelerating as quickly as possible, is a cone. Apollo figured that out. Orion uses it again. But Orion is larger, substantially larger. The Apollo command module had an interior volume of roughly 210 cubic feet. Orion's pressurized volume is about 690 cubic feet, more than 3 times as much. This matters when you are planning missions that could last weeks or months, when 4 people need to live, sleep, eat, exercise, conduct science, and maintain their physical and mental health in a space the size of, as one description puts it, a large camper van. The habitable volume, the space you can actually use as opposed to the space occupied by equipment, is about 330 cubic feet. Still small, still intimate in a way that would make most people profoundly uncomfortable, but workable, livable, for 10 days at least. The Orion service module, built by the European Space Agency, provides the spacecraft's primary propulsion, electrical power, and water and air systems. It uses a modified version of the main engine from the Space Shuttle's orbital maneuvering system, a technology that was tested and proven across 135 shuttle missions, another example of how spaceflight accumulates knowledge across generations. The service module's solar array wings, 4 of them, deployed after reaching orbits span about 67 feet and generate enough power to run the spacecraft systems continuously throughout the mission. The heat shield. Let us spend some time on the heat shield because it is one of the most technically demanding components of the entire vehicle, and because it will be important later in this story. The Orion heat shield is approximately 16.5 feet in diameter, larger than any heat shield ever flown on a human spacecraft. It is made of avcoat, an ablative material, which means it protects the crew not by resisting heat in the way a conventional insulator might, but by slowly burning away. As the outer surface of the heat shield heats to thousands of degrees during re-entry, the material chars and vaporizes, and in doing so, it absorbs and carries away enormous amounts of thermal energy that would otherwise penetrate into the vehicle. The burning surface of the heat shield effectively becomes its own cooling mechanism. The material is sacrificed so that the crew can survive. For the Apollo missions, avcoat was manufactured as a honeycomb structure, filled cell by cell with an epoxy mixture. For Orion, the manufacturing process was modernized. Blocks of avcoat are now bonded to the underlying aluminum structure, rather than filled in place. This sounds straightforward, but it created a new engineering challenge that became apparent during the uncrewed Artemis I test flight in November 2022. The boundaries between blocks showed unexpected ablation patterns, meaning the material wore away unevenly in ways that the pre-flight models had not fully predicted. The heat shield performed adequately, the spacecraft returned safely, but the data raised questions. Questions that the Artemis II mission, with its human crew and suite of tracking cameras and monitoring systems, was specifically designed to help answer. We will return to what those answers revealed. The spacecraft also carries 32 cameras, including instruments with lenses capable of capturing photos or video, mounted both inside the crew cabin and on the exterior of the vehicle. 15 are fixed to the spacecraft itself. 17 are handheld cameras operated by the crew. This is not just for the spectacular photography that made headlines around the world during the mission. These cameras serve an engineering purpose. They document, in real time and with unprecedented resolution, exactly what happens to the spacecraft during every phase of the mission. What does the heat shield look like during re-entry from 100 miles away, as tracked by aircraft? What do the parachutes look like when they deploy? What does the service module separation look like from inside the capsule? Every piece of footage is data. Every image is a data point in the relentless, meticulous project of learning how to keep people alive in space. April 1st, 2026. Launch Day. There is a tradition at NASA for crew wake-up calls. A song chosen by the crew or selected by mission control to start each day of a mission. The tradition goes back to the early shuttle era. On launch morning, the Artemis II crew woke to the song, Run to the Water, by the band live. If you know that song, if you know those opening chords, that slow build, those lyrics about finding something true in the hardest places, then you understand something about the emotional texture of this mission that no amount of technical description can convey. They rode out to the launch pad in the crew transportation vehicle. They suited up in the Neil Armstrong Operations and Checkout Building at Kennedy Space Center, the same building where Apollo crews prepared before their missions. They rode the elevator to the top of the launch tower, walked the crew access arm, and one by one, they climbed into integrity. Reed Wiseman took the left seat at the primary controls. Victor Glover to his right. Christina Koch and Jeremy Hansen behind them. The hatch was sealed. The countdown clock ran. At 6:35 p.m. Eastern, the core stage's RS-25 engines, 4 of them modified versions of the engines that powered the Space Shuttle main propulsion system for 3 decades, ignited, and a half-second later, the 2 solid rocket boosters lit. The combined thrust of all 6 elements of the Space Launch System is, as I mentioned, 8.8 million pounds. The Saturn V rocket that sent Apollo to the moon produced 7.5 million pounds of thrust. The SLS is more powerful. It is the most powerful rocket ever successfully flown by NASA. The stack cleared the tower in seconds, cleared the launch pad, cleared the cloud layer, and within 8 minutes, the core stage had burned through its propellant, separated, and fallen back toward the Pacific Ocean where it burned up in re-entry. The interim cryogenic propulsion stage, the upper stage, fired to insert Orion into an elliptical orbit around Earth, reaching an apogee of about 46,000 miles. And then the crew went to work. Because even in these first hours, even before they had begun to fly away from the Earth in earnest, there was a program to verify and a test flight to conduct. Christina Koch and Jeremy Hansen unstrapped from their seats and began testing life support systems. The water dispenser, the firefighting masks, the toilet. The toilet, famously, presented some initial difficulties. It is a detail that makes every engineer in mission control grit their teeth slightly and every human being watching from Earth smile in recognition. Because even in the most advanced spacecraft ever flown by NASA, plumbing is still plumbing. Koch fixed the issue. The mission continued. The crew then performed a manual piloting demonstration, testing Orion's handling qualities by flying it by hand, with the empty ICPS upper stage as a practice docking target. This was not a trivial exercise. One of the primary objectives of Artemis II was to verify that the Orion spacecraft handles correctly in the actual deep space environment, where the radiation levels are higher, the thermal gradients are more extreme, and the communications latency is longer than anything experienced in low Earth orbit. A spacecraft that handles beautifully in simulation may behave differently when it is actually 40,000 miles from Earth, in a thermal environment that causes structural components to expand and contract in ways that ground-based testing can only approximate. Christina Koch, during a post-flyby communication with NASA, described the experience of manually piloting Orion in deep space as astonishing. She said the control algorithms were extraordinarily precise, and that watching the vehicle respond when they deliberately degraded its thruster performance, simulating a partial system failure, was one of the most surprising and gratifying parts of the entire mission. It flew. Even broken, it flew. After the piloting demonstration, the crew configured for the translunar injection burn, the engine firing that would break them free of Earth's orbit entirely and put them on a course for the moon. This burn lasted approximately 6 minutes. 6 minutes of engine fire, aimed with extraordinary precision, accelerating Orion and its crew to a speed sufficient to escape Earth's gravitational dominance and fall, gradually, under the growing influence of the moon's gravity, 239,000 miles away. It had been 54 years since anyone had done this. The journey to the moon takes about 3 days. 3 days of traveling through what NASA engineers call the cislunar environment, the space between the Earth and the moon, which sounds nearby on a solar system scale but is, in human terms, an enormous and largely empty and deeply hostile region. The radiation levels are higher than those experienced on the International Space Station, because beyond the protection of Earth's magnetosphere, the crew is exposed to galactic cosmic rays and solar energetic particles that the space station largely avoids. The communication delays, while not yet the minutes-long gaps that Mars missions would face, are real and measurable. The thermal environment cycles more dramatically between the intense heat of direct sunlight and the cold of deep shadow. Orion carries an experimental payload called Avatar, an acronym for a suite of biological experiments that includes bone marrow cells derived from crew blood samples. These cells are being used to study how the human immune system responds to the deep space radiation environment. This is not an abstract academic exercise. One of the primary medical challenges of long-duration lunar surface missions and eventual missions to Mars is radiation exposure, and specifically, the risk of radiation-induced immune system dysfunction that could leave astronauts vulnerable to infections or cancers that would otherwise be manageable. Avatar is gathering real data from a real deep space environment, and that data will directly inform the design of radiation shielding, mission profiles, and medical countermeasures for every crewed mission that follows. The crew also conducted a 24-hour acoustics test, measuring the sound environment inside the cabin continuously for an entire day. This sounds trivial but is actually a significant human factors consideration. Extended exposure to noise levels above a certain threshold, even moderate noise that does not feel uncomfortable, causes cumulative hearing damage and sleep disruption. Sleep deprivation is one of the primary contributors to human error in complex technical environments. If the spacecraft is too loud during sleep cycles, the crew sleeps badly. If the crew sleeps badly over a multi-week lunar surface mission, performance degrades in ways that are hard to model but catastrophic in their consequences. Knowing exactly what the acoustic environment is in the actual deep space thermal conditions allows engineers to optimize insulation and damping systems for future vehicles. On flight day 4, as Orion was approximately 169,000 miles from Earth and closing on the Moon, the crew woke to the song Pink Pony Club by Chappell Roan, and Victor Glover took manual control of the spacecraft to conduct another deep space handling qualities test, providing additional data on Orion's performance at a greater distance from Earth, in slightly different thermal and radiation conditions. Each test, each data point, each anomaly noted and characterized is a brick in the foundation of the Artemis II mission that follows. On flight day 5, Orion performed a trajectory correction burn, a 17.5-second firing of the service module engine to refine its path to the Moon. Of the 3 planned correction burns, this was the only one executed. The navigation was accurate enough that the other 2 burns were unnecessary. The precision of deep space navigation in 2026 is, frankly, astonishing. The engineers at NASA's Jet Propulsion Laboratory, using a network of large dish antennas called the Deep Space Network stationed at Goldstone in California, Madrid in Spain, and Canberra in Australia, can determine the position of a spacecraft 250,000 miles away with an accuracy of better than a few hundred meters. They can calculate the exact trajectory correction needed to hit a target window over the lunar surface roughly the size of a city block. This is not guesswork. This is geometry, physics, and decades of accumulated precision. April 6, 2026. Flight Day 6, the day that changed everything. At 12:37 in the morning Eastern Time, on the boundary between the 5th and 6th days of the mission, Orion entered what is called the lunar sphere of influence, the invisible boundary in space where the Moon's gravity becomes the dominant force acting on the spacecraft rather than Earth's. At that moment, the spacecraft was no longer, in the strictest dynamical sense, orbiting the Earth. It was falling toward the Moon. Christina Koch, awake and monitoring the transition, said to Mission Control, "We are now falling to the Moon rather than rising away from Earth. It is an amazing milestone." She was right, but the milestone was about to get much bigger. At 12:56 in the afternoon Central Time, the Artemis II crew surpassed 248,655 miles from Earth, the distance record set by the crew of Apollo 13 in April 1970. That record had stood for 56 years. Apollo 13, as you may recall, set that record not in triumph but in emergency. An oxygen tank in the service module exploded 2 days into the mission, crippling the spacecraft's power and life support systems. Jim Lovell, Jack Swigert, and Fred Hayes had to shut down the command module, retreat into the lunar module, a spacecraft designed for 2 people for 2 days, not 3 people for 4, and use the Moon's gravity to sling them around and back to Earth without ever being able to perform the lunar landing they had trained for. They were 248,655 miles from Earth at their farthest. They were running out of power, water, and air, and they made it home. The record they set was a record of survival. The Artemis II crew broke that record. They surpassed it not in emergency but in triumph, not clinging to a damaged spacecraft but riding a fully functional one, not fleeing the Moon but approaching it deliberately, scientifically, with 32 cameras recording every moment. Jeremy Hansen spoke from the cabin of integrity. From the cabin of integrity here, as we surpass the furthest distance humans have ever traveled from planet Earth, we do so in honoring the extraordinary efforts and feats of our predecessors in human space exploration. We will continue our journey even further into space before Mother Earth succeeds in pulling us back to everything that we hold dear. But we most importantly choose this moment to challenge this generation and the next to make sure this record is not long-lived. Not long-lived. That sentence is a gift to the future. It is an astronaut, in the most distant moment of human spaceflight, looking further ahead and saying, "We must go farther." The record we are setting right now should not stand for another half-century. It should fall quickly because we should be going further, always further, and the only way that happens is if we commit to it. Orion continued its approach, and at approximately 5:47 in the afternoon, something happened that only Apollo mission controllers had experienced before in the context of human spaceflight. The Deep Space Network lost contact with the spacecraft. Not because of a technical failure, because the moon got in the way. Orion had passed behind the moon. For approximately 40 minutes, the lunar surface, a ball of rock 2,159 miles in diameter, sat between integrity and every human being on Earth. The moon, which we have been staring at for the entirety of recorded human history, which we have named craters and seas and mountains on, which has pulled our tides and inspired our calendars and given sailors a lamp and given lovers a symbol, the moon was blocking the signal. During those 40 minutes, the crew was completely alone. Not in the way that people mean when they say they feel alone at 3 in the morning, unable to sleep, staring at the ceiling. Alone in the cosmically literal sense. On one side of the moon, 8 billion human beings, all of their civilizations and conflicts and music and grief and hope. On the other side of the moon, for people in a capsule called Integrity, traveling at 3,139 miles per hour relative to the lunar surface, watching features of the far side of the moon that no human eye had ever directly observed pass below them. The far side of the moon. Let me tell you about the far side of the moon, because it is stranger than most people realize. The moon is tidally locked to the Earth, which means it rotates on its axis at exactly the same rate that it orbits us, so it always presents the same face toward Earth. This is not a coincidence. It is the result of billions of years of gravitational interactions that gradually slowed the moon's rotation until it synchronized with its orbital period, a phenomenon called tidal locking that is common throughout the solar system. The moon's near side, the one you see on a clear night, the one with the man in the moon patterns that humans have been projecting personalities onto since we first stood upright, has been mapped and photographed and studied extensively. The far side was a complete mystery until 1959, when the Soviet Luna 3 spacecraft photographed it for the first time. And what those photographs revealed was remarkable. The near side of the moon is dominated by dark, flat regions called Maria, from the Latin for seas, named by early astronomers who thought they might actually be bodies of water. These dark plains are ancient lava flows, evidence of a period of intense volcanism billions of years ago, when the moon's interior was still hot enough to melt rock and push it to the surface. The far side has almost no Maria. It is almost entirely highlands, cratered, ancient, bright. The crust on the far side is thicker than on the near side, which may explain why the volcanic lava flows did not punch through as easily. The topography is more extreme. The craters are, if anything, more numerous and more dramatic. It is a more ancient-looking landscape. And during those 40 minutes of communications blackout, the Artemis II crew were the first human beings to see it with their own eyes. Not through the cameras of a robotic spacecraft. Not through a telescope. With their own eyes. Through the windows of Integrity at closest approach, approximately 4,067 miles above the farside surface. Christina Koch described the color nuances she observed, subtle variations in the gray of the regolith, hints of brown and tan in certain crater walls, the way shadows stretched dramatically from crater rims across the surface in the oblique sunlight. These observations, gathered by 4 pairs of human eyes looking at a landscape that no human had ever directly seen, were received by the science team at Mission Control with, as one mission scientist described it, grins, nods, and lots of chatter. The human eye is a remarkable scientific instrument. It perceives color gradients and textures and 3-dimensional structure in ways that no automated camera system has fully replicated. When a geologist looks at a rock formation, they bring decades of pattern recognition to bear in a fraction of a second. When Christina Koch and Victor Glover and Reed Wiseman and Jeremy Hansen looked at the far side of the moon, they were bringing the full capability of the human visual system, integrated with the knowledge of trained astronauts and scientists, to a landscape that had never before been observed by anyone. Then Orion emerged from behind the moon, and the crew, who had just passed through the shadow of the moon, now witnessed something that no human being had witnessed since the Apollo era. Earthrise. The moment when the Earth, blue and white and impossibly beautiful and impossibly small against the darkness, appeared above the lunar horizon. The famous Earthrise photograph taken by William Anders during Apollo 8 in 1968 became one of the most influential images in human history, widely credited with catalyzing the environmental movement, with changing how humanity thought about the fragility and preciousness of our home world. It showed us, for the first time, that the Earth is an object. A finite, bounded, singular object in a very large and otherwise mostly empty space. And here were 4 human beings watching that image appear, not in a photograph but in real time out a window 250,000 miles from home. When the Deep Space Network reacquired Orion's signal and contact was restored, the crew reported their observations and shared their imagery. The science team at Johnson Space Center received the data with what can only be described as sustained professional joy, the particular satisfaction of people who have worked for years toward a moment and then watched it actually happen, better than they had allowed themselves to hope. But Flight Day 6 was not finished. Toward the end of the 7-hour flyby observation period, something rare happened. Orion, the Moon, and the Sun aligned in such a way that the crew experienced a total solar eclipse from space. The Sun disappeared behind the mostly dark Moon. For almost an hour, the crew looked at the solar corona, the Sun's outermost atmosphere, the gossamer plasma halo that extends millions of miles from the solar surface but is ordinarily invisible because the Sun itself is too bright. During a total eclipse, the corona becomes visible to the naked eye, and it is one of the most breathtaking sights available to human perception. The crew of Artemis II saw it from 250,000 miles away, from the perfect vantage point of the lunar flyby geometry. They photographed it. They watched for flashes of light from meteoroid impacts on the darkened lunar surface. Small impacts that release brief flashes visible from hundreds of miles away, providing data on the flux of impactors in the lunar environment. They looked for planets visible in the corona's vicinity: Venus, Mars, Saturn, temporarily revealed by the eclipse's darkness. The mission science officer, Dr. Kelsey Young, speaking to the crew after the flyby, said, "I can't say enough how much science we've already learned and how much inspiration you've provided to our entire team, the lunar science community, and the entire world with what you were able to bring today. You really brought the moon closer for us today. You brought the moon closer for us today." That sentence deserves to be engraved somewhere permanent. During the flyby, the crew also did something deeply personal, and I want to spend some time with it because it reveals something important about what human space exploration means beyond the engineering and the data and the national prestige. They suggested naming 2 craters on the moon. The first crater they proposed to name, Integrity, after the spacecraft that carried them, after the word they chose to put on the hull before they left Earth. It is, in a sense, the most modest kind of immortality, a name on a geological feature on another world, a name that will persist long after the spacecraft itself is a museum piece and its crew are remembered only in history books. The second crater, in honor of Carol Wiseman, in honor of Reed Wiseman's wife who died in 2020. Taylor, as she was called, the woman who never got to see her husband fly to the moon. There is now a crater on the moon named for a woman who died before this mission happened. There is now a mark on the surface of our nearest neighbor that carries the name of a person who was loved and missed and remembered and honored with the most extraordinary gesture available to the person who loved her. A man who flew around the moon and named a piece of it after her. I do not know what Taylor Wiseman believed about the universe or about what happens after we die or about whether the dead can somehow know the things that the living do in their memory. Nobody knows those things. But I know this. Reed Wiseman's daughters will grow up knowing that there is a crater on the moon with their mother's name on it. They will know that their father carried her with him to the farthest place any human being has ever traveled. And that knowledge, that fact about the universe, belongs to them now, permanently, irrevocably, forever. The journey home took 3 days. 3 days of increasingly detailed preparation, of trajectory correction burns, of system monitoring, of cabin reconfiguration for re-entry. On Flight Day 8, a planned manual control test was canceled so that engineers could gather additional data on a small helium leak detected in the service module's propulsion system. This is exactly the kind of thing a test flight is designed to find. The leak was small enough that it posed no safety risk to the crew. But its presence, its behavior, its rate, its response to different thermal conditions, provided data that will inform the propulsion system design on future Orion service modules. You do not discover this kind of information without flying. You can model and simulate and test in a chamber, but the actual deep space environment will always surprise you, and the only way to learn what it does to your hardware is to fly your hardware in it. On Flight Day 9, Orion performed a 9-second trajectory correction burn to refine its return path. The remainder of the day was spent on cabin preparations, stowing equipment, installing the crew seats in their re-entry configuration, reviewing re-entry procedures in careful detail, because what was coming next was, in many ways, the most dangerous part of the entire mission. On Flight Day 10, April 10th, the crew woke to the song Free by Zac Brown Band. At 2:53 in the afternoon Eastern Time, Orion conducted its final trajectory correction burn, an 8-second firing that locked in the precise re-entry corridor over the Pacific Ocean. At 7:33 in the evening Eastern, the service module, the European-built propulsion and power unit that had carried the crew from Earth to the Moon and back, separated from the crew module. It was immediately committed to atmospheric re-entry on its own, where it burned up as designed, adding its mass to the Earth's atmosphere in molecules and ash. The crew capsule, now alone, the 4 astronauts inside it trusting entirely in a 16.5-foot heat shield and a system of 11 parachutes, reoriented itself. The heat shield turned forward. The spacecraft positioned for fire. At 7:53 in the evening, Orion officially entered Earth's atmosphere. The plasma formed. The signal went dark. The 6-minute blackout began. I want to describe what is happening inside mission control during those 6 minutes. Because it is not nothing. It is not calm. The flight directors and the capsule communicators and the systems engineers and the flight surgeons, people who have trained for years, people who have run this scenario in simulation hundreds of times, people who know exactly what is happening at every moment of the re-entry profile, those people are still, in those 6 minutes, just people. They are not omniscient. They cannot see inside the plasma sheath. They cannot verify in real time that the heat shield is performing as modeled, that the structural temperature gradients are within limits, that the parachute mortars are intact and primed. They can calculate what should be happening. They cannot observe what is happening. Howard Hu, NASA's Orion program manager, described watching for the main parachutes to deploy as his favorite moment of the mission. He said he was chanting, quietly, by himself, "Go, go, go." The man who is professionally responsible for the vehicle that is returning for human beings from the moon was chanting, alone, because there was nothing else left to do. The engineering was done. The preparation was done. The math was done. Now it was just the physics and the heat shield and the parachutes and time. The drogue chutes deployed at 22,000 feet altitude. 2 of them pulling the capsule stable, stopping the tumble, orienting integrity correctly for the main chute deployment. At 6,000 feet, the 3 main parachutes opened, each one 116 feet across. 3 of them, red and white and enormous, blossoming above the falling capsule like a declaration of survival. The capsule decelerated from 300 miles per hour to approximately 20 miles per hour in minutes. From a speed that would kill you to a speed that, while not comfortable, is survivable. At 8:07 in the evening Eastern Time, on April 10, 2026, the Orion spacecraft named Integrity splashed down in the Pacific Ocean, approximately 60 miles off the coast of San Diego, California. The total distance of the journey, 694,481 miles. The duration, 9 days, 10 hours, and change. The cost, in terms of human willingness to accept risk in service of discovery, immeasurable. Mission Control announced, a new chapter of the exploration of our celestial neighbor is complete. Integrity's astronauts back on Earth. The recovery operation is a choreography of extraordinary precision, and it deserves more attention than it typically receives in the coverage of these missions. The USS John P. Murtha, an amphibious transport dock ship of the United States Navy, 684 feet long and capable of carrying large volumes of equipment, aircraft, and personnel, had been positioned for days in the recovery zone. The ship's well deck, a flooded compartment in the stern that can be used to launch and recover watercraft and amphibious vehicles, was configured to receive the Orion capsule after splashdown. Navy small boats carrying divers and medical personnel had been deployed as many as 12 to 14 hours before splashdown, waiting at predetermined positions. The recovery team had rehearsed the recovery sequence many times. They had protocols for every contingency: rough seas, capsule instability, crew injury, equipment failure. This is the first time since Apollo 17 in December 1972 that the United States Navy has been called upon to recover a crewed spacecraft returning from the vicinity of the moon. 54 years. An entire generation of sailors had never done this. The knowledge of how to do it had to be rebuilt. from the records of the Apollo program, from simulation, from practice operations, from consultation with the handful of people still alive who actually did it the last time. This recovery was not just a logistics operation. It was an institutional revival. Before the crew could be extracted, a team designated Sasquatch, I am not making this up, had mapped the zones of the Pacific Ocean where jettisoned hardware would land. The forward bay cover, the drogue parachutes, the parachute mortars. These pieces of hardware fall separately from the capsule, and the recovery boats and helicopters need to know where they are so they do not accidentally drive through a falling heat shield cover. Navy divers entered the water before Orion finished splashing down. They attached lines to the capsule. They secured an inflatable collar around its base to provide stability in the swells. And then the hatch opened. Reed Wiseman came out first, then Victor Glover, then Christina Koch, then Jeremy Hansen. Each of them, assisted by recovery personnel, moved carefully, with the slightly tentative movements of people who have been weightless for 9 days and are only now relearning the language of gravity. After 9 days in 0G, the vestibular system has recalibrated. The fluid in the inner ear has redistributed. The muscles that spend their waking hours resisting gravity have rested. Standing up is, at first, a negotiation. Walking on a moving ship deck is a significant physical challenge. The crew had taken anti-nausea medication before re-entry and were consuming extra fluids and electrolytes to counteract the fluid redistribution that happens in microgravity, where fluids shift from the legs toward the head and the body reduces its total fluid volume in response. Coming back into gravity means the legs need that fluid back, and the cardiovascular system has to readjust quickly, or the astronaut will feel dizzy, lightheaded, and nauseous. Within 2 hours of splashdown, all 4 crew members were aboard the USS Mirtha. Medical personnel were waiting on the flight deck as each helicopter delivered its astronaut. The crew underwent post-mission medical evaluations, assessments of cardiovascular function, muscle strength, balance, vision, and cognitive performance, among other things. 9 days in deep space, beyond the protection of the geomagnetic field, with elevated radiation exposure and the biomechanical changes of microgravity, produces measurable physiological changes. Some of them are temporary. Some may require monitoring over longer timescales. Understanding exactly what those changes are and how they vary between individuals is one of the critical medical science objectives of the Artemis program. NASA flight surgeon Rick Schuring described on the live broadcast what the transition back to gravity would feel like for the crew. I worked with all the Apollo astronauts years ago, and they all told me that landing in water, particularly the Pacific, can be very provocative. Provocative. That is the careful medical language for a physical experience that most human beings would describe rather more colorfully. The following day, after medical evaluations aboard the ship, the crew departed by helicopter to San Diego, and from there continued to NASA's Johnson Space Center in Houston, where their families were waiting. The expected arrival at Ellington Field was between 3 and 8 in the afternoon Eastern Time on April 11th. This reunion, the moment when 4 people who had been around the moon came home to the people who had been waiting for them, is not scientifically quantifiable. It does not appear in mission reports, but it is, in many ways, the true ending of the mission. The moment when the astronaut stops being the crew member of integrity and becomes, again, a parent, a spouse, a friend. Now the engineering questions. Now the things that happened on this mission that will directly shape every mission that follows. The heat shield. After splashdown, Navy divers photographed the heat shield from the water, the first imagery of the Orion heat shield's condition after a crewed lunar return re-entry. 2 heat shield experts from NASA's Johnson Space Center were already aboard the USS Mirtha before Orion was even pulled from the water. When the capsule was recovered into the well deck, a process that typically takes 4 to 6 hours after splashdown, they conducted immediate visual inspections. Howard Hu, the Orion program manager, said, "We gathered a lot of data. When we get the crew module into the well deck, we'll do some inspections right off the bat." Aircraft equipped with cameras tracked the capsule during re-entry and gathered the first imagery of the heat shield's performance during the plasma phase. After the capsule is transported back to Kennedy Space Center, engineers will conduct detailed scans of the heat shield, looking for the ablation patterns, the boundary behavior between blocks, the thickness measurements at hundreds of points across the surface. This data will feed directly into the design and manufacturing specifications for the Artemis II heat shield. If the Artemis I data raised questions, the Artemis II data will provide answers. Not complete answers, perhaps, but enough to make decisions, to refine models, to fly again with greater confidence. The service module's helium leak. Small, not safety critical, but real. The data gathered on its behavior during the mission will inform a valve redesign for future service modules. This is the nature of flight test programs. You find the things that are not quite right, not catastrophically wrong, but worth improving. You improve them. You fly again. The toilet. Christina Koch fixed the toilet issue on launch day. There are still further improvements to be made before Artemis III. This is perhaps the most humanizing fact in the entire mission manifest, and I want to linger on it for a moment, because I think it says something true and important about the entire enterprise of human spaceflight. We are sending people to the moon. We are doing things that require the combined intellectual output of tens of thousands of engineers, scientists, technicians, and support staff. We are flying the most powerful rocket ever built by NASA. And one of the engineering challenges on the manifest is make the toilet work better. Because human beings are biological creatures who require food, water, sleep, and functioning waste management systems, regardless of how far from Earth they have traveled. The physics of orbital mechanics does not grant exemptions for physiology. The moon does not care about your plumbing, and your plumbing does not care about the moon. For people in a spacecraft need a toilet, and the toilet needs to work, and making a toilet work reliably in zero gravity, in the thermal environment of deep space under the vibration loads of re-entry, is a genuine engineering challenge that receives very little glamorous coverage but must be solved nonetheless. NASA's Associate Administrator Amit Kshatriya, speaking at the post-splashdown news conference, addressed the tight turnaround for Artemis III. Flight cadence and iteration is the key to reliability and safety. We try to make sure the machine is perfect. Keep flying, keep learning, keep getting data in the flight environment. We need that muscle memory to exist. We need the data to keep coming in. We need to quickly iterate and change the mission as we learn from it right after. Keep flying, keep learning, keep getting data. That is the philosophy. It sounds obvious. It is, in practice, extremely difficult. Every flight costs money. Every flight carries risk. Every delay is politically vulnerable. The temptation always is to wait until you are certain, to not fly until you have solved every problem, answered every question, eliminated every uncertainty. But the only way to eliminate certain kinds of uncertainty is to fly. The environment of space is irreducibly different from any environment on Earth. The only data that matters is flight data, and flight data can only be gathered by flying. Let me talk about Artemis III, because Artemis II was not the mission. It was the bridge to the mission. Artemis III, currently targeted for 2027, has been restructured. Originally, it was planned as the first crewed lunar landing since Apollo 17. An updated program structure in early 2026 revised this to make Artemis III another demonstration mission, focused on testing the rendezvous and docking procedures between the Orion spacecraft and the commercial lunar landers being developed by SpaceX and Blue Origin. Artemis IV is now the targeted landing mission. This is the patient approach, the infuriating, necessary, historically vindicated patient approach. The Apollo program killed 3 astronauts in a launchpad fire during Apollo 1 in 1967, and the program was delayed for nearly 2 years, while investigators understood what happened and redesigned the command module. The Space Shuttle program was grounded for 2.5 years after the Challenger disaster in 1986, and again for 2.5 years after Columbia in 2003. Every time a program has rushed past its uncertainties instead of resolving them, the bill has come due in ways that could not be afforded. The Artemis program is choosing, deliberately and at political cost, to go step by step. To land on the moon when every system needed to keep people alive on the moon has been tested and understood and improved. Not before. The commercial lunar landers are central to this plan. SpaceX's Starship HLS, the human landing system variant of the Starship vehicle, is designed to carry astronauts from lunar orbit to the surface and back. Blue Origin's Blue Moon lander is being developed as an alternative. Neither of these vehicles has yet landed a crew on the moon. Artemis III will test the docking procedures. Artemis IV will attempt the landing. Each step tests something. Each step reduces the uncertainty carried into the next. And somewhere in the training facilities at Johnson Space Center right now, a crew is preparing to do what no human being has done since December 1972. Land on the moon. We do not know their names yet. We will know them soon. And when they descend in the lunar lander toward the surface, when the dust blows out from the landing engine and the feet touch down and the first person climbs down that ladder and puts a boot print in the regolith, they will be doing it because Artemis II happened, because integrity flew, because Reed Wiseman and Victor Glover and Christina Koch and Jeremy Hansen accepted the risk, gathered the data, flew around the moon and came home, and handed the program everything it needed to go further. I want to spend some time now on the question of why. Not the programmatic why, not the political rationale or the budget justifications or the geopolitical competition with China's lunar ambitions. The deeper why. The why that is harder to articulate but that, I think, actually drives the whole enterprise. Why does it matter that human beings go to the moon? There is a pragmatic answer that is perfectly defensible. Because the moon contains resources, water ice at the poles, rare earth elements in the regolith, helium-3 that could theoretically be used in fusion reactors, that have potential economic and technological value. Because a lunar presence is a necessary stepping stone to Mars, providing a location closer than Earth where deep space systems can be tested and supply caches can be established. Because the technology development required to send humans to the moon generates spin-offs, medical devices, materials, communication systems, software, that improve life on Earth in ways that are difficult to predict and impossible to fully account for in advance. These are real reasons. They are insufficient. There is a scientific answer, because the moon is a pristine record of the early solar system, preserved in its ancient craters and its regolith, holding clues to the formation of the Earth, the origin of water in the inner solar system, the history of solar activity over billions of years. Because a geologist walking across the lunar surface, examining rocks in place with their own hands, making real-time decisions about which samples to collect based on what they see, can accomplish in a week what it would take a robotic rover years to achieve. These are real reasons. They are also insufficient. There is the inspiration argument, because a generation of young people who watch astronauts walk on the moon will be motivated to pursue careers in science, technology, engineering, and mathematics. Because the investment in human potential that a visible, dramatic, national commitment to exploration represents pays dividends across decades in the form of a more scientifically literate, technologically capable population. This is real. It is documented. It happened after Apollo, and it will happen again. It is still insufficient. The sufficient answer, I think, is something that does not fit neatly into a budget justification or a congressional hearing transcript. It is this: we are the only species on this planet, and quite possibly the only species anywhere in the observable universe, that has developed the capacity to deliberately expand our presence beyond the world of our origin. We are the only creatures that can look up at the moon and say, "We will go there," and then go. This capacity, this particular combination of intelligence, ambition, technical ability, and collective organization, emerged from 4 billion years of biological evolution on a single small planet. It is extraordinarily rare. It may be, for all we know, unique. To possess a capacity and not use it is a kind of death. Not a dramatic death, not a sudden one, but a slow dimming of something that once burned. The civilizations that stopped exploring, that reached the boundary of the known world and turned back, decided that what they had was enough, chose safety and familiarity over the risk and reward of the unknown. Those civilizations did not flourish. They stagnated. They were eventually surpassed by those who kept going. We went to the moon between 1969 and 1972. We stopped. For 54 years, we circled our own planet, never quite leaving, never quite staying, building a space station and launching probes and mapping Mars with robots, always deferring the larger ambition. And on April 1st, 2026, we left again. For human beings climbed into a capsule called Integrity and flew to the moon. Not to stay, not yet, but to go. To show that we can still do it. To gather the data needed to stay next time. To place a boot print in the direction of everywhere we have not yet been. The astrophysicist Carl Sagan, in his book Pale Blue Dot, wrote about what the Voyager 1 photograph of Earth from 4 billion miles away meant, what it should mean, what it demands of us. He wrote about our responsibility to be kinder to one another, more compassionate, more aware of the fragility of the only home we have ever known. He wrote about the long history of human longing to explore, to push beyond the known, to find what lies over the next hill. He wrote about the stars. Neil deGrasse Tyson, whose voice, whose style, whose approach to communicating the wonder of the universe at the intersection of science and human meaning is the spirit of this channel, has spent decades making the same argument in different forms. That the universe is not indifferent to us, it is simply vast, and our response to its vastness should not be paralysis but curiosity. That the fact of our cosmic insignificance, the fact that we live on a mote of dust in an unremarkable corner of one of 2 trillion galaxies, is not a cause for despair but for wonder. We are the universe looking at itself. We are the mechanism by which the cosmos has become aware of its own existence. That is not nothing. That is, in fact, everything. When the Artemis II crew flew around the moon and looked back at the Earth, when they saw our whole world, all 8 billion of us and everything we have ever built or destroyed or loved or feared, contained in an object small enough to cover with a thumb held at arm's length against the black, they were doing something that very few human beings in history have been able to do. They were seeing us from outside. They were seeing the planet as an object, a finite bounded object suspended in space, with no protective atmosphere visible at that distance, no political borders, no indication from that vantage point that the surface below is home to an extraordinary diversity of human cultures, languages, histories, and stories, all of which are, from that perspective, inseparably part of the same small, fragile, astonishing whole. The overview effect. Astronauts have described it again and again. Edgar Mitchell, who walked on the moon with Apollo 14, said it felt like an instant of global consciousness. A sudden, wordless, intuitive understanding of the connectedness of all things. Ron Garan, who spent time aboard the International Space Station, wrote about looking down and seeing both the extraordinary beauty of the planet and the heartbreaking contrast between that beauty and the suffering of billions of people on the surface below. Frank White, who coined the term, collected testimony from dozens of astronauts who described a profound shift in their perception of what matters, of what is important, of what deserves our protection and our effort and our love. For more people have now had that experience. Reed Wiseman, who carries grief and love in equal measure and raised 2 daughters while flying to the moon. Victor Glover, who represents a correction, a long overdue declaration that the future of exploration belongs to all of humanity. Christina Koch, who spent 328 days in space before spending 9 more flying around the moon and said, during that flyby, that she was not ready to come home. Jeremy Hansen, who carried his family's birthstones to the farthest place any human being has ever traveled and brought them back. For more people who have seen the Earth from the outside. For more people who know, now, in a way that is not merely intellectual but physical and visceral and permanent, that the things that divide us are small and the things that unite us are enormous. Let me tell you about a small stuffed animal. Every crewed spacecraft carries a zero-gravity indicator, a small, lightweight object that floats freely when the spacecraft reaches weightlessness, providing the crew with a simple, immediate, visual confirmation that they are truly in microgravity. On the International Space Station, crews have used plush toys, tiny flags, small mascots of various kinds. On Artemis II, the zero-gravity indicator was a stuffed figure called Rise. Rise was designed by an 8-year-old named Lucas Yee from Mountain View, California. It was selected from over 2,600 submissions from more than 50 countries, including entries from K-12 students around the world. The design was inspired by the Apollo 8 Earthrise photograph, the most famous photograph ever taken from space, the image that first showed Earth as a small bright ball rising above the lunar horizon. Lucas Yee's design depicts the moon wearing Earth as a baseball cap. The figure was fabricated by NASA's Thermal Blanket Lab at the Goddard Space Flight Center and tethered inside the crew cabin of Integrity. An 8-year-old child from California. An image inspired by a photograph taken before any of the crew of Artemis II was born. A stuffed mascot floating in a spacecraft 250,000 miles from Earth. If you want to understand what the Artemis program is for, not the technical objectives, not the budget justifications, not the geopolitical competition, if you want to understand the human meaning of it, you can start there. With Lucas Yee and his drawing of the moon wearing Earth as a hat. With the fact that 2,600 children from 50 countries drew pictures for this spacecraft. With the fact that NASA, for all of its institutional complexity, made room in the manifest for a stuffed animal designed by a child, because it understood that the thing being carried into space was not just a capsule but a symbol, and symbols need to mean something to the people who witness them. Every one of those 2,600 children who submitted a design knows, now, that they can be part of this. That space is not just for people who went to MIT or flew F-18s or spent their 20s in graduate school doing orbital mechanics. It is for everyone who looks up. It is for everyone who wonders. It is, in the deepest sense, a human project. So what comes next? The Orion capsule will be transported from the USS Mertha back to Kennedy Space Center in Florida. Engineers will conduct detailed post-flight inspections, detailed scans of the heat shield, analysis of every data channel recorded during the mission, inspection of the parachute system, evaluation of the service module's helium leak, assessment of every anomaly noted during the 10 days. The data gathered will be cross-referenced with pre-flight models and simulations, and where the models were wrong, where reality diverged from prediction, the models will be updated. This is how you learn, not by assuming you already know, but by comparing what you predicted to what actually happened and revising. Artemis III is coming. The exact manifest is still being finalized, but the mission profile involves Orion rendezvousing with and docking to a commercial lunar lander in lunar orbit, testing the procedures that will be required for Artemis IV's landing mission. The crew for Artemis III has not yet been announced. They are training somewhere right now, running simulations, learning the orbital mechanics of a specific cislunar docking sequence, practicing the contingencies. They will be announced. They will have their press conference. They will talk to their children about what they are about to do. And eventually they will climb into an Orion spacecraft, a spacecraft that has flown twice now, that has proven itself in the fire of re-entry and the cold of deep space, and they will launch. And then Artemis IV, and the lunar surface, and the first human boot prints in the regolith since December 1972. And the first woman to stand on the moon, and the first person of color, and the beginning of what NASA has described as a sustained human presence on the moon, not flags and footprints, not a brief visit followed by 50 years of absence, but a real presence with habitats and research facilities and systems that accumulate knowledge across missions and years. And beyond that, Mars. Not soon. Not within the next decade, almost certainly. But the trajectory is clear. The architecture of Artemis, the heavy lift rocket, the deep space capsule, the commercial landers, the orbital rendezvous capabilities, is the same architecture that will be adapted and extended for Mars. Every mission is a step. Every step carries the next one. The question is not whether we will go to Mars. The question is when and what it will cost and who will be in the first crew and what will they find there. We are at the very beginning of the second era of human deep space exploration. Think about that sentence. We were in the first era from 1968 to 1972, 4 years, 12 flights beyond low Earth orbit, 12 men on the moon. Then we stopped for 54 years. Now we have started again. And this time, the ambition is not to plant flags and collect rocks and come home. The ambition is to stay. The challenges are enormous. The radiation environment on the lunar surface, stripped of Earth's magnetic protection, bombarded by galactic cosmic rays and solar energetic particles, poses real health risks over extended stays. The regolith itself, the fine gray dust that covers the entire lunar surface, is sharp and abrasive at the microscopic level because unlike Earth dust, it has never been smoothed by wind or water, and it gets into everything. Equipment, suits, air filters, lungs. The thermal environment cycles between minus 250 degrees Fahrenheit in the shadowed craters of the South Pole and plus 250 degrees Fahrenheit in direct sunlight. The communications delay with Earth, about 1.3 seconds one way for the Moon, compared to 3 to 22 minutes for Mars, is manageable on the Moon but will require new operational philosophies for deep space. The psychological challenges of isolation and confinement, already well studied from Antarctic and ISS research, will intensify as distance and duration increase. None of these challenges are insurmountable. All of them are understood well enough to be addressed systematically. The question is whether we will do the work, whether the political will, the funding, the institutional commitment, the public engagement, and the human courage will all persist long enough and clearly enough to get the job done. April 10th, 2026 gives us reason to believe they will. Because here is what that splashdown represented. 3 orange and white parachutes opening above the Pacific Ocean 60 miles off San Diego. A small capsule descending at 20 miles per hour out of a sky that it had just crossed at 25,000. For people alive inside it, carrying between them the experience of the far side of the moon, the farthest place any human being has ever been, the solar corona framed by the lunar edge, the Earth rising above the gray horizon of a world that is not our own. A crater named Integrity. A crater named Carol. A spacecraft that went around the moon and came back and brought its crew home. This is what we can do when we decide to do it. This is what happens when the mathematics is right and the engineering is sound and the training is sufficient and the will is present and the 4 people inside the machine are the people who should be inside it. When all of those things align, the impossible becomes a splashdown in the Pacific Ocean on a Friday evening. When all of those things align, the news is, we went to the moon and we came back and everyone is alive. We went to the moon and we came back and everyone is alive. Repeat that. Let it settle. Consider how much human effort, human knowledge, human sacrifice, human courage, human genius, and human stubbornness is encoded in that sentence. Consider that it was not obvious it would be true. Consider that the engineers who built Orion, the mission controllers who flew it, the flight directors who made every real-time decision during those 9 days, the recovery divers who were already in the water before the capsule hit the surface. All of them were betting their professional lives and their personal integrity on a chain of physical events that had to unfold correctly, in sequence, without catastrophic failure, for 694,481 miles. And it worked. Not perfectly. Nothing works perfectly. There was a helium leak and a toilet problem and heat shield data that will require careful analysis and a valve that needs to be redesigned and parachute system details to be reviewed and medical data to be studied. That is what test flights are for. That is the whole point. You fly to learn. You learn to fly better. You fly again. But the mission objectives were met. The crew is alive. The data is in. Artemis II is coming. And somewhere, right now, an 8-year-old child is watching footage of 3 parachutes opening over the Pacific and deciding, for the first time, that they want to be an astronaut. Somewhere, right now, a girl is watching Christina Koch step out of the crew hatch and deciding, for the first time and without fully understanding why, that the thing she thought was impossible for people who look like her is not actually impossible. Somewhere, right now, a child in Toronto or Lagos or Jakarta or Sao Paulo or Bangalore or Seoul is watching Jeremy Hansen or Victor Glover come home from the moon and feeling the first stirring of something that will, 2 decades from now, drive them into a career in engineering or planetary science or materials science or medicine, and they will carry with them, as background radiation of their professional lives, the memory of seeing a person who looked like them or came from a country like. They're standing next to a spacecraft that had been around the moon. This is what space exploration does. Not just to the people who fly, to the people who watch. The moon is waiting. It has been waiting, patient and gray and absolutely unchanged by our absence, for 54 years. It will wait as long as necessary. It will be there when Artemis IV lands. It will be there when the first lunar base is established. It will be there when the first human beings leave the surface and point their spacecraft toward Mars, knowing they are beginning the longest journey our species has ever attempted, knowing that the moon behind them is the training ground, the stepping stone, the first beyond-Earth place that human beings learn to live on. And the moon will be there, patient as it has always been, when they look back and see it receding in their windows, smaller and smaller until it is just another bright object in the sky. And somewhere in that moment, I hope someone aboard that Mars-bound spacecraft will think about integrity. About a 9-day mission in April of 2026. About 3 parachutes over the Pacific. About a record set by Apollo 13 in 1970 that stood for 56 years and was broken not in emergency but in triumph. About a crater named for a late wife. About a stuffed mascot designed by an 8-year-old from Mountain View, California. About the moment when we started again. This is CosmHush. Stay curious. Look up. Always, always look up. The universe didn't wait for us to be ready. It never does. We go anyway. That's what we do. That's what we've always done. And now, after 54 years, we're doing it again. Integrity's astronauts back on Earth. And then back to the stars. But let me go deeper into something that I think gets lost in the headlines. Something that is easy to miss when you are watching the parachutes open and the capsule hit the water and the crowds cheer in mission control. The science. The actual lunar science. Because Artemis II was not just an engineering test. It was simultaneously a genuine scientific mission. And what the crew saw during their 7 hours of lunar observation, the things they described in real time with their own voices to scientists on Earth, deserves more attention than it typically receives in the coverage of these events. David Kring is a planetary geologist at the University Space Research Association, and he has been studying the moon for his entire career. He gave basic geology training to all 4 Artemis II astronauts before the mission. When Victor Glover was flying 4,067 miles above the lunar South Polar region and calling down descriptions of the topography he was seeing, describing crater walls and ridgelines and shadow-filled valleys and the dramatic relief of features that Kring had been trying to explain in classroom sessions for years, Kring said he could hear Glover finally getting it. "The elevation changes are greater than the elevation of Mount Everest on Earth," Kring said. "And I could hear Victor finally getting it." That sentence about a scientist who has spent decades studying a place hearing an astronaut finally get it, in real time from space while flying 4,000 miles over the place being studied. That is a moment that only exists in human spaceflight. A robotic spacecraft could not have that moment. A satellite cannot call down to mission control and say, "Oh, now I understand." Only a person can do that. Only a trained human mind encountering a landscape directly, with all of its pattern recognition and contextual knowledge and capacity for wonder, can make the kind of real-time connection between what it is seeing and what it knows that changes understanding. Kelsey Young, the Artemis II lunar science lead, said something at a news conference that I want to quote carefully. "The human eye, especially when it's connected to a well-trained brain, which I assure you these 4 people have, is capable of just in literally the blink of an eye making nuanced color observations." Color observations. Let me explain why that matters. The color of a rock tells you what it is made of. And what a rock is made of tells you how it formed, and when and under what conditions. On the lunar surface, the Maria, those dark flat plains on the near side, are made primarily of iron and magnesium-rich basalt, erupted from the interior billions of years ago. The highlands are made of older, lighter-colored anorthosite, a calcium-rich rock that crystallized from the magma ocean that covered the entire early moon. When the crew reported seeing browns and blues and subtle greens in addition to the expected grays, when they described color variations that, as Young noted, can reveal mineral composition and geological age, they were gathering data that photographs alone cannot fully capture. A photograph flattens the color response. The human eye, adapted to parse color under a wide range of illumination conditions, and connected to a brain that can instantly recognize the significance of an unexpected hue in an expected context, to something that no current camera system can fully replicate. Victor Glover, during the flyby, was particularly